So today's lesson is about exponential growth and decay, and we're going to focus on just the graphs aspect of it today. And so by the end of the lesson, you should be able to say that I can model exponential growth and decay using tables, graphs, and equations. And today it's mainly going to be focused on graphs. Now, to start today, we have a warm-up. So consider the number of toothpicks used to create the images below. Write an equation, create a table, and a graph for the pattern. So think about how many toothpicks are in each of these, what the equation would look like, and go ahead and graph, and then come back and check your solution against mine. So when analyzing the number of toothpicks in the image, in the first one, there's 3 toothpicks. In the second one, we have 5 toothpicks, and in the third one, there's 7 toothpicks. So because it's going up by 2 each time, I know right away that it is a linear relationship. So I know that my equation that I write has to be linear. And it's going to be y equals 2x plus 1. Now when I graph it, it does turn out to be linear. It's a nice straight line. Y intercepts at 1, has a slope of 2, and it's a linear graph. So remember, when you analyze the number of toothpicks, or if you analyze images like this, they could be linear or exponential, and we've dealt with that in the past. Next, go ahead and look at these examples. We have to determine if they're linear, exponential, or neither. Looking at number 1, I see that the p is going up by timesing by 5 every time. So because I'm timesing by 5, I know that that's going to be exponential. Exponential. And actually my equation would be y equals 5 to the x. Here, in the second one, that x is our exponent, so we know that's going to also be exponential. Down here, we have an mx plus b kind of thing going on, so this is going to be a linear graph. And our final example, it's actually adding 20 each time, so that's going to be linear. And the equation would be y equals 20x plus 5. Now really getting into exponential growth and decay models. We know that the functions can be modeled by y equals a times b to the x. Now, we've dealt with typically equations that look like y equals 5 to the x or 3 to the x or something like that. However, there is this a part we cannot forget about when we really delve into growth and decay functions. A, it actually represents your initial amount. Right. So it's what you're starting with, okay? Initial amount is at A. The b then, that's raised to the power of your x, is going to be your common factor. So that's what you're growing by or decaying by. It's your growth or decay factor. So here in that last slide we had it growing by a factor of 5. So our common factor was a 5 in that case. So when looking at exponential growth and decay a little closer, we have to first consider what our initial amount is going to be. For both growth and decay, your initial amount has to be greater than 0. So A is greater than 0. And the same is for decay. A is greater than 0. So that means in both cases, A is going to be a positive number of some kind. It can be a decimal, it can be a whole number, but it's going to be positive. If it is a negative number, then it still could be exponential. It just would not be growth or decay specifically, because it would be on the bottom half of our graph. It would be in quadrants 3 and 4 versus 1 and 2. Now, going to exponential growth, if we think about our growth factor for exponential growth, it's going to be 1 plus the percent of your rate of change. And remember, percents have to be in decimal form. And so what's going to be here is your b, or your growth factor, is going to be greater than or equal to 1. Now, looking at decay, here's where things are a little different than growth. Here, rather than going 1 plus your rate of change, you're going to actually do 1 minus the percent of your rate of change. And your percent, like in growth, has to be in decimal form. And so your decay factor in exponential decay equations is actually going to be between 0 and 1. 0 is going to be less than b, but b is going to be less than 1. And so basically if you have a decimal or a fraction of some kind, it's going to be decay. And then if you have a whole number, so 1 or greater, it's going to be growth. Notice they're always positive once again. If for some reason you would have a negative number, then it could still be exponential. It just would not be a growth or decay exponential function. So, directions on this next slide say that we need to identify our initial amount, A. We need to identify the growth or decay factor, B. Then we need to label it as either growth or decay function. So, looking at our first example, 14 is our initial amount, A. 2 is our growth factor of B. And now because A is greater than 0, and our growth factor is greater than 1, this is a growth function. Looking at this next one, 25,600 is our A. 1.01 is our B. And because they're both positive and B is greater than 1, it's going to also be a growth function. Go ahead, try the next two examples on your own and label them as growth or decay. So looking at our next two examples, A was 5 and 0.1, B was 0.5 and 0.9, and they're actually both decay functions. And they're both decay because our B is less than 1. That's what we really need to focus on when we're trying to determine growth or decay. If it's less than 1, or between 0 and 1, it's decay. If it's 1 or more, it's going to be growth. So on this next slide, we have to graph our function. We have to identify the initial amount, the growth or decay function, and if it's either a growth or decay function overall. So our initial amount is always the A, and y equals A times b to the x. However, looking at here, this is our b to the x. Our A is actually just a 1. So our initial amount A is just a 1. Our common factor, that b, though, is 1.5 in this case. And then let's go ahead and make our table and graph before we determine if it's growth or decay. Knowing that b is 1.5, I'm going to assume growth, but let's just double check. So we put our x and y in, and I like the points -2, -1, 0, 1, and 2. So go ahead, find your y's and graph, and then let's come back and see. So looking at my table, I have 1 over 2.25, which is about 0.4, and 1 over 1.5, which is about 0.67. And then I have my values, and I graphed, and I spaced my graph out a little more, but it is still at right shape. It's exponential for sure. It's going upwards, so it is definitely a growth function that I have here. And I knew that because this b was greater than 1, so I was right initially, and my graph looks correct. Our next problem says that Loon Lake has a killer plant problem. There is currently 2,000 square feet of the lake is covered with a plant. The area covered is growing by 50% each year. Growing, that's an important word. So we have to label A, B, write an equation, make our table, and graph. So it's growing by 50%, so we for sure know it's going to be a growth function. So if our graph doesn't show growth, we did something wrong. A, remember, is our initial amount. It says currently there's 2,000 square feet. Our initial amount is 2,000. Our B is our growth. It's growing by 50%, so it's going to be 1 plus 0.50. So our B function is going to be 1.5. Now when we write our equation, it's going to be y equals, or f of x equals, a, so 2,000, times 1.5 to the x. A times b to the x. Now we need to make our table, x and y, and see what happens when we graph. So go ahead and do that on your own. So when we plugged in values into our table, we currently have 2,000 square feet, so we really don't need to plug in negatives. And so I plugged in 0, 1, 2, 3, 4. I found the corresponding values. They were increasing because this is a growth function, which is exactly what our graph shows. And notice how I had a number and label my graph so that it fit nicely and I used my space wisely. Last but not least, the paper chart starts with has an area of 64 square inches. That sounds important. That's what we started with. Complete the table to show the area of a ballot after each of the first 10 cuts. Write an equation to model the situation and then graph. So remember, with our equation, we're going to need A, or the initial value, the growth factor, or decay factor, and then our equation, which we can say is y equals. So go ahead, fill in your table, come up with your A, B, and your equation, and go ahead and graph. So looking at this, 64 to 32, 32 to 16, we're dividing by 2. That's what I thought of initially. So dividing by 2. However, the problem is you can't get the decay or growth factor from dividing. You have to think of, okay, dividing by 2 is multiplying by what? I know it's multiplying by a half. So my decay factor, because it's decay graph, is going to be 0.5. Because we're multiplying by a half each time. Our initial value is at 64 start point. And so our equation is y equals 64 times 0.5 raised to the x power. And notice that each time we divide by 2 or multiply by 0.5, our numbers get smaller and smaller. You can see that on the graph. We have a quick decay, goes down very quickly the more folds we make, and then once we get to the end, it's all very, very small. And technically, if we're looking at this graph right here, we never actually cross this x-axis. It comes close, it looks like it's maybe even touching, but we're technically not crossing or even touching. It's just kind of leveling out according to our vision.